Next talk is by Eli Visbal, who will talk about the impact of feedback processes on POP3 star formation.
Okay. Thank you very much to the organizers. This is a really wonderful conference so far. For anyone who doesn't know me, my name is Eli Visbal. I'm an assistant professor at the University of Toledo. Today I'm going to discuss some work I've recently completed with Greg Bryan and Zoltan on using semi-analytic models to understand how feedback processes affect population 3 star formation. So I want to begin just with a motivation for using semi-analytic models as a computational approach. We've heard a lot today about, well, some about semi-analytics, but also a lot about hydrodynamical cosmological simulations. These are a very important tool to understand the formation of the first stars and galaxies, in particular because they can have a very detailed, sophisticated treatment of of many important physical processes, such as the chemistry of primordial gas, cooling, collapse of gas, even radiative transfer of ionizing radiation through the intergalactic medium. The main disadvantage of simulations, though, is that they're computationally expensive. For instance, the Renaissance simulations, we have a figure on the right here from this suite of simulations, took millions of CPU hours to run. And because of this expense, it restricts the amount of volume, cosmological volume, or redshift range we can cover when performing these simulations. And even though the treatment of physics is very sophisticated, some subgrid physics is still required, and this leaves us with free parameters. For instance, the initial mass functions of POP3 or POP2 stars, or in some simulations, the transition from the critical metallicity for the transition from POP3 to metal-enriched star formation. And so it can be challenging to explore the entire parameter space of this physics in the high redshift universe with just hydro simulations alone. So it's complementary if we also have fast alternative approaches, and semi-analytics fits that description. So I'm going to describe a model we've recently put out. It is based on cosmological n-body simulations. And so we extract merger trees and, importantly, the 3-dimensional positions of the halos in the simulations. So we actually do include the full clustering of all the halos in our semi-analytic model. Once we have these positions and merger trees for the dark matter halos, we can apply analytic prescriptions to determine where POP3 stars form, as well as where the first galaxies in metal-enriched star formation occurs. And so we include the important processes for POP3 star formation, including H2 photodissociation due to Lyman-Werner radiation. We include metal enrichment, like we just discussed in the previous question and answer from the previous excellent talk. But here we actually include external metal enrichment bubbles and the clustering of nearby halos, how one galaxy or cluster of POP3 stars in one halo can pollute with supernovae winds nearby halos with metals. We also include the inhomogeneous ionization of the intergalactic medium. And finally, we include the baryon-dark streaming velocity. So these are very computationally efficient. They run quickly on one core. Here is just a snapshot of one of our models. In a 5 megaparsec box, we have on the left all of these are the halos above 10 to the 6 solar masses, and then on the right we show which halos are either hosting population 3 or metal-enriched star formation. All right, so I don't have time to discuss all of the details of the physical prescriptions we put in the models, but I just wanted to mention briefly how we handle these 3-dimensional clustering effects. So we've developed a new grid-based method where essentially we distribute all of the halos in our simulation box on a grid. And this allows us to use essentially the convolution theorem and fast Fourier transforms to quickly compute the feedback processes that depend on the separations between various halos, including Lyman-Werner feedback, external metal enrichment, and reionization, And so this allows us to figure out which halos should be hosting POP3 versus metal-enriched star formation. And so here are some projections from one of our simulation boxes. It's a 3 megaparsec box at redshift 8.6. On the left, we see which halos are hosting POP3 versus metal-enriched star formation. In the center panel, we see the metal bubbles due to supernovae winds that have propagated throughout the intergalactic medium. And so this is the projection of parts of the simulation that are enriched sufficiently that you would have POP2 and no longer have POP3 star formation. And then on the right, we show the projection of the reionization bubbles at the same redshift, which also impacts where stars can form, because reionization photoheats the gas and can make it hard to form stars in small dark matter halos. Okay, so because this model is very computationally efficient, we went through and explored the parameter space to determine how different physics affects mainly the star formation rate density, both in population 3 stars and metal-enriched stars. And so we can both check how different model parameters affect these quantities, as well as turning off various feedback prescriptions one by one to see how things build up to create the final star formation rate densities we see in our models. So here I plotted the star formation rate density as a function of redshift, both for population 3 in the lower curves and metal-enriched. This is a case where we varied the star formation efficiency in population 3 star-forming halos. And so this is just one example of varying one of the parameters in our model. But I just wanted to, at first, just go over some of the broad brushstroke results we see. Generally, we see a transition from POP3 to metal-enriched star formation quite early on in our simulations. The exact redshift of this transition depends on the precise prescription, but it happens very early always. And then another thing we see is most of our models see persistent population 3 star formation to the end of our simulations at redshift 6. And so I'd say this is an important takeaway result. I'd also say that following the 3D clustering of halos and their spatial distributions seems to be particularly important below a redshift of about 15. And this is because at higher redshifts, the metal bubbles in our prescription, as well as the reionization bubbles, are so small that even with the bias clustering of halos, we don't, the spatial positions of the halos make less of a difference. Okay, so I just want to then show a couple more results from our models. So let's start with external metal enrichment. We have a relatively simple prescription. We assume that after stars form, supernovae push metal bubbles out with a constant velocity up to some maximum radius. Then we have a free parameter that allows us to vary the size of these bubbles. And we also have a free parameter for the critical metallicity, where you have a transition from POP3 to metal-enriched star formation. And so here I plotted the POP3 star formation rate density and metal-enriched for varying these different parameters. And we can see that in our fiducial model, we have this persistent population 3 star formation down to redshift 6. But if you increase the size of the bubbles by a factor of 2 and reduce the critical metallicity, you can really begin to quench POP3 star formation at this redshift of 6. So we believe that there's likely to be this persistent POP3, but it is sensitive to the details of external metal enrichment. The one last, so I don't have time to go over very many of our results, but the last one I'm going to summarize is the impact of reionization. So as I mentioned, ionization photoheats gas. It increases the minimum mass of halos that can form stars efficiently. And so we've looked at how this affects the star formation rate density in our model. Here we've plotted our fiducial model, and then for comparison in red, a case where the escape fractions are reduced by a factor of 3. So this would basically be if reionization happened much more slowly and was much weaker, we can just ask what would happen in that case. And we found it quite surprising initially that it didn't seem to change the star formation rate density in our simulation. But when we went and looked at individual halos, we were able to understand what was happening much better. So here are plots showing individual POP3 star formation events in our fiducial model, as well as the case where we've weakened reionization. And so this shows the mass of a halo where POP3 stars form is a function of redshift. And it turns out that the total POP3 star formation is similar in both of these runs, but the main difference is where the POP3 star formation occurs. So when you turn off, or when you turn down reionization, lower the escape fraction, you have very few regions that are ionized. So you get most of the star formation occurs at the atomic cooling limit, which is this dashed curve. You have fewer halos where star formation is suppressed all the way up to this higher mass, which is what we've assumed for the minimum mass in an ionized portion of the intergalactic medium. And so this was an interesting observation, and it mainly has to do with our assumptions about having a constant star formation efficiency in all of our halos, as well as the shape of the halo mass function. And another sort of broad point that this makes for us is that that as we march from the very early universe down through the epoch of reionization, it should be generically true, and as we know, that we should transition from POP3 star formation mainly being in mini halos to either atomic cooling halos or pristine halos that were ionized and then collapse and star formation occurs in even more massive halos than the atomic cooling limit. And so I think this type of result motivates additional simulations for these sort of lower redshift POP3 star formation in either atomic cooling halos or even more massive halos. So we looked at other physics such as supernovae feedback. I'm running out of time, but I'll just point out that we assume the metal-enriched star formation occurs in a halo after POP3 with some delay due to having to recover from a supernovae explosion. And we find that when you change this delay time, you can very dramatically shift when you get a transition from metal-enriched dominating, which is these top curves, rather than metal-enriched dominating at very early redshifts. It can move to lower redshifts when metal-enriched star formation dominates over the population 3. So that brings me to the end of this presentation. I think I'm out of time exactly, so I will leave my summary and conclusions up here. But the one thing I did want to say is I wanted to advertise a postdoctoral position. I'm hoping to hire a postdoc at the University of Toledo starting next fall to work on topics related to the high redshift universe, including possible topics could include the first stars, first supermassive black holes, or studying the new technique of measuring the large-scale structure in line emission with galaxy line intensity mapping. So I'd encourage anyone who's on the job market or knows anyone to keep an eye out for this ad, which will appear on the job register next week. So thank you very much.
Thank you, Eli, for a nice talk. Actually, you stimulated a very large number of questions on Slack. So I think I'm just going to ask one of them, and then you're encouraged to answer them on Slack. The question asked by Rafael Schneider is, well, nice work. Your POP3 star formation rate density at redshift below 6 seems to flatten. Why is the star formation rate density in POP3 stars not dropping due to reionization?
So essentially what happens, so the reason why we maintain a flat star formation rate density is that we essentially have halos that are below this critical metallicity down to road. So pristine, or even if they're not pristine, low metallicity halos that are low enough below the threshold we've set. And so really you essentially, a generic thing we generally find is reionization bubbles are larger than the metal bubbles for our for what we thought was a realistic prescription. And you'll reionize pristine halos, delay the star formation, and then depending on how big the metal bubbles are and the threshold for transitioning from pop 3 to pop 2, either those metals will catch up with and essentially pollute before star formation can occur. But if, depending on the exact values of those parameters we put, if the metal bubbles don't expand far enough, you'll still be able to make pop 3 stars in those pristine massive halos where reionization delayed star formation, but eventually the halo gets big enough that it does make pop 3 stars.
Okay, thanks, Eli. So please answer the rest on Slack.
Okay.